This is the next video in the chapter on atoms, molecules, and ions. So far in the story of Harry Potter and the evolution of atomic theory, we have looked at the atom from Dalton's perspective and from Thomson and Millikan's perspective with the electron having been discovered. So next we are going to look at what happens when the proton is finally discovered. When we finally figure out what happened to that positively charged blob in the center of the atom. So stay tuned. So we need a new research question. We now know what things are made of. And we also know what is inside the atoms that things are made of. There are electrons in there, but we're not quite sure about that positively charged blob that we drew in the center. We don't have any concrete evidence for that. So where is the positive charge in an atom? That's what we really want to know. As you notice about scientists, they're never happy when they've answered one question. They find a new question that they really want to know the answer to, and they start working towards that. So our next question is, where is the positive charge? So our next champion was named Rutherford. And we'll look at Rutherford's gold foil experiment. So Rutherford's experiment involved a radioactive substance. And this radioactive substance produced radioactive particles. And these particles just happen to have positive charge. Positive charge. So this is a radioactive source in a box because they're dangerous. So this is going to be our radioactive source. Very nice. And it's in a box with a slit in it, so only a thin stream of particles being emitted by that radioactive source is able to make it out. So it's kind of like a laser beam of positively charged particles. So let's see, we used red for positive charges. So this is going to be positively charged particles. And these actually have a name. These are called alpha particles. You can write it as the word or as the Greek letter. And these alpha particles are positively charged and fairly small. All right, so we're trying to find the positive part of an atom, so we're going to use a positively charged particle to try and look for it, because what we learned from the experiments about the electron was that when you want to find negatively charged particles, you shoot negative things at it and wait for it to bounce. So we're going to do the same thing. We're going to shoot positively charged things and wait for it to bounce off of the positively charged inside of an atom. So the thing that those positively charged particles are being shot at was a very thin piece of gold foil. You may know gold is one of the heaviest atoms that exists. Those are pretty heavy atoms making up that foil sheet. And so these positively charged particles were shot at this piece of gold foil to see what happens. So whenever you do an experiment, you have to have a prediction about what you think might happen. And we can guess what Rutherford's prediction was based on the current view of the atom at the time. So the current view was the plum pudding model of the atom. There were small, negatively charged particles called electrons inside of an atom, randomly distributed, and the rest of it was positively charged. But instead of having one charge over one small area, there were 4 charges over a very large area. So this huge atom had a couple of charges that were widely distributed in the predicted theory. So what they figured was, when we have this stream of alpha particles and we're aiming it at gold, and the alpha particles are full of positive charges, we're going to have a small, dense positive charge, and we're going to be hitting a large distributed positive charge. And since this charge isn't very dense, and this charge is, then these charges will likely pass mostly straight through. They might be deflected a little bit, maybe like 15 degrees out to the side or something. But this is not a very highly positively charged molecule. And so we didn't predict there was going to be much of a deflection. So the way we can figure out where these alpha particles go is with a luminescent screen. So when an alpha particle hits this screen, the screen will light up. So if we have a particle that goes through and hits the screen right here, you'll be able to see a flash of light. And that's how we can tell where the particles go and how much they're deflected. So this is a luminescent screen, which basically means that it glows when something hits it. So, prediction. According to the plum pudding model, or the chocolate chip cookie dough model, positively charged alpha particles that came out of that radioactive source are predicted to pass through the gold sheet undeflected. They should go right through the gold atoms. But one important part of being a scientist is realizing that your hypothesis is just a guess and that it could be wrong. And that so when you design your experiment, even though you think most of the particles are going to hit right in the center of the screen, maybe a little bit to the side, you should be open to the fact that your hypothesis could be wrong. And you should measure data to prove that your hypothesis was right or wrong. So Rutherford did something that was very important, was he, instead of putting the screen only directly behind the foil in the path of the beam, he tried to put the screen all the way around the beam to measure, to look for particles that had bounced off in any direction. Even though he didn't expect to see any particles over here or over here, he put the screen there just to check. And then he sat in a dark room for a very long time and watched particle after particle after particle pass mostly straight through the foil and occasionally to the side, as he had predicted. But after sitting and watching this for many, many hours, he noticed that every few hours there was one occasional particle which would be completely deflected off to the side. Not just like 10 degrees or like 15 degrees, like huge, huge bounce. 150-degree bounce off to the side. And this was just a slap in the face to this researcher. A quote from his journal describes it as, "It was as if I shot a bullet at a piece of tissue paper and the bullet bounced back and hit me in the face." It was a complete surprise to see these tiny positive charges bounce as if they'd hit a baseball. So that meant that the hypothesis and our prediction wasn't quite right. And as we showed in our scientific method flowchart, if your evidence doesn't support your hypothesis, then you have to modify it. You have to make a change. So we have to change what we think an atom looks like. Oh, we should add our observation first. So when we shot the alpha particles, most of the particles passed through the gold undeflected. Here we go. But a few of them were deflected by a lot. And it was a complete surprise. So we have to modify our view of the atom to adjust for that. So we know we've got an atom, and we know we've got this beam of positively charged particles that are going into it. And what we witnessed was that most of these alpha particles passed straight through and didn't encounter a significant positive charge. They didn't hit anything that would cause them to bounce. But some of the beams did hit something. They passed into the atom and they bounced. And they came out and hit the screen at a totally unexpected direction. And so that means that if such a major bounce happened, that a positive charge is being repelled by something strongly positively charged. So that meant there was a very small, very strongly positively charged something inside of this atom that caused this major bounce to happen. So down here in the reality section, we observed that there must be a very small, very dense, positively charged center. And because it was the first time we had discovered something, it had to have a name, and it was named the nucleus. So a very small, very dense, positively charged nucleus at the center of a mostly empty atom. We know the electrons are there. We discovered them already. But remember that the electrons were very, very, very small and very light. So they don't take up much space in this atom either. All right, here's our new vocabulary word, the nucleus. So that nucleus was the center, and it was positively charged, and that meant that there was some sort of a positively charged particle inside that nucleus at the center, and so that particle needs a name too. So the nucleus contains positively charged particles. And we needed to call them something. And we'd already named the negatively charged particles electrons. So we just picked something that named with that had a P for positive, and we called them protons. Because why not? So positively charged protons that were much, much heavier than electrons. And there's our new vocab word. So after that slap in the face, we really need to amend our picture of what an atom looks like, because now it no longer needs to look like a plum pudding model. We need to make sure there's a nucleus in our new picture. So let us go back to our what does an atom look like log and update it for 1911. So log entry 1911, headline, Rutherford discovers the nucleus and protons inside of it. Okay, so we're going to have a really different looking picture now. Here's our big atom. We know there are going to be some small negatively charged bits somewhere orbiting it or inside of it or something. That part's still not quite clear yet. And now we know that there's going to be a positively charged center. And that positively charged center is going to contain positively charged particles called protons. So we'll circle around that. So this is our very heavy nucleus containing positively charged protons. And the rest of this is 99.9% empty space. Empty space is the part that the alpha particles pass through mostly undeflected, but if the alpha particles hit the nucleus, they would bounce off. So our view now contains a nucleus, protons, electrons, and atoms. And there are a few more parts that we're going to add to our picture of an atom in the next video.